As we're going to begin animating objects around on the screen, right now in Object Move we have a div which has a class of box assigned to it. We'll see that it has a position of fixed, it has a height and width on it, gets colored red, and it gets put behind everything else. So temporarily I am going to comment out a line here, and now we'll take a look at the project, and we'll see that it just puts a red box in the upper left corner of the page. Now that red box did have its CSS set as fixed so that it stays in place while the text can scroll over it, and it sits behind the text because it has a z index of -1. If we don't have that z index on there, we'll see that it sits on top of the text, and well, that's not very good. Now you could, if you used fixed elements on your page, you can use that for fixing navigation bars and things like that, so you permanently lock them on the top of your screen so that as people scroll past, the navigation is always present. Or you could lock a footer or both. So you can use fixed as a way of displaying things on screen. I'm using it to send it to the background. That's why I use the -1. If we use position absolute instead of fixed, we'll see it looks similar, but then as the page scrolls, its position is absolutely set at, well, 0, 0 plus the native padding of the elements on the screen. So we don't really want that. Now, if I go into this document and I uncomment out one line that I had commented and save it, we'll see that what's happening is, I'm going to refresh the page so we can see it starts, and oh, that red box is animating itself across the screen. And it's disappearing. Oops, that's a problem. So that's something that we need to fix. But before we worry about fixing it, we're going to talk through a little bit of what's happening with the JavaScript code behind this. When we are animating elements on screen, we can animate the numerical properties of objects. So that means anything that has a number associated with it, which includes color, position, scale, rotation, transformation options, such as skewing and 2D and 3D transforms. All of these things are numeric in how they are measured, and because of that, we can animate that number. If we animate that number, we give it a changing value, the object is going to change that property on screen. In this particular instance, I am grabbing a hold of the object with the box class associated with it. I am then going to find the current left position of that object. And that's what the getBoundingClientRect does. So that allows us to find the left edge of the object on screen. Then I'm going to compare that current left position of the object and find out, is it less than the inner width of the window? So the window is my viewport, this area here. Now I'm looking for, is that position of object less than this edge here, or the width of my window? And if so, I'm going to increase the box position. Then I will manually set the style and update that using our template literal, which I'll talk about that shortly. Otherwise, we reset the box's position. But what you will notice is when we run this, the box is not resetting because there's a little issue in the code. So I've provided with you the first version of the code that I wrote, and then when it didn't work, I looked and went, oh yeah, whoops, that was silly on my part. And then I had to fix it. So we're going to let you fix the code in a moment, but I want to talk about the template literal right here. A couple things that are happening with this as we look at it. It is not using standard single quotes. Instead, we are surrounding text with. So this is a backtick. It is not a single quote, and it behaves a little bit different. So if we use backticks, and we can use backticks in place of single quotes, and I believe almost, I haven't figured out where you can't. But if we use a backtick, then what I can do I can string my variable together by putting it inside of curly braces, preface it with a $sign, and then I have my variable and then my text I want to put with it. The alternative way of writing this, if we did use quotes, is I would say box POS plus PX, like this. So this is equivalent to this. And both are good, but if you start stringing together more than one variable with other text, it sometimes becomes easier to read it if you use a template literal. And again, we use the backticks, $sign, and curly braces around it. That is how we designate we're using a template literal instead of a standard concatenation of a string using our variable, the plus sign, and then putting the text inside of quotation marks. Either one do work, and I could use either one. The template literals are the more common with modern JavaScript, so we're seeing it more and more in more situations, so it's something you should get used to doing. Keep in mind that the $sign here does not have any reference to jQuery. So we've used jQuery in the past where the $sign referenced jQuery. The $sign here has nothing to do with jQuery. If you look through the document, you'll see that jQuery is not being used or loaded anywhere. So this $sign is purely being used as a template literal. So continuing with this, we have our two versions of how we could do it. We could use the old method, or we could use the template literal, and both work. I don't really care what you use, so you could go this way or the other way. But what does matter is moving down the screen to the final line in the function. And the final line in the function says window.requestAnimationFrame, and in parentheses RAQ. Now if you notice, RAQ happens to be the name of the function we're currently in. requestAnimationFrame is the best way to do animation right now inside of web browsers because it goes at the speed of what that particular device can handle. It gives you the best bang for the buck and the best performance. It also has a couple of other nifty features built into it. If you use set timeout or set interval as a way to animate or move objects around on screen, so you create moments of time, and at every moment of time you make something happen, which is what animation is. If you do it the old way, you run into problems in that if the machine can't handle it, it gets chunky. And if the machine goes to, say, a different tab or window in the browser, that timer or interval is going to keep going and eating up processor power, memory, battery, and all those fun things. Request animation is set up that if it's not the current active tab or window in the program, it will throttle itself down to essentially nothing to help conserve battery life. So requestAnimationFrame is the preferred way of generating animation content or any time-based content that we need. If we wanted to build a game inside of our web browser, we would use requestAnimationFrame as our game clock to help power that program so that it's performing on a regular interval and updating the assets on screen, doing whatever other computations are necessary to play that game. The way requestAnimationFrame works is we call it, and then we call the function that we want to run again. In this case, we're running ourselves. So it creates this loop. It goes through, and then at the end of requestAnimationFrame, it says, oh, I'll go call that function. It calls requestAnimationFrame again, and it now creates a loop. Typically, it runs at about 60 frames per second, which is a solid frame rate for animation and games. And we trigger it by calling it at the very end because our script runs, but the function doesn't happen until it's called. So we call it at the end, and then this function just keeps looping indefinitely. There's a cancel animation frame command that we could use as well. So we could cancel it if we so chose. So we could set up a button, or we could make something that would cancel that animation. So say we were building a game and on the loading screen we don't have the animation running, and then we click play, we go and play the game, and then when we're done playing the game we cancel animation frame when we go to then the game over screen. So it's a way to help conserve our resources on the device. It would be considered a polite way of working and something that you should entertain. Now when this runs, the box goes and it goes, and then it goes off screen and it never comes back. So the first thing we have to do is figure out where the thinking went wrong in this code. With the box flying off the screen, we need to adjust one line of code to fix it. If we look at what's happening, we take box position, we add 5 to it, then we set the box's position based on that. Now if I log this out and take a look at what's happening, we'll see how the number goes up and up and up and up and up, and then the numbers stop going up. And that kind of makes sense, because if I look at what's happening here, if the box position is less than the width of the window, we add to it, then we set the box's position. But if the box's position is not less than the width of the window, then we're going to try and call this line here. But what we've never done is reset box position. So we're never fixing what was there and moving it around. So all we have to do is take this line of code and move this out of here so that now the box position gets updated, or it gets set here, which we could even just make this so that we just set BOS equal to -200. That would work as well. Now if we go, we'll see that the number goes up, and oh, should have fixed it. Change 2 lines. We update box position, or we set it to a negative value so it goes to the left of the screen, and then we update our box position. So with this, we're able to animate the box. Now, animating CSS properties, while is doable, can be a very tedious way of working with things, but there are a lot of possibilities you can do, because with JavaScript we can animate any numerical property. So right now I'm modifying the left position of the object as it moves around on screen. So we're setting its style left position, which in the beginning we never set it, so it defaulted to its natural position of wherever it was going to start on screen. If we wanted to, we could say left and just set it at a different value, and it starts then in the middle of the screen, and now it moves itself over. So anything with a number we can be animating. We can animate the size of an object, height and width, we can animate positions, we can animate colors, and any other transformable property with a number can be adjusted. So we can do it, and there are a lot of JavaScript libraries out there that people have made that help you to animate any of these numerical properties of objects. Working with the canvas is super fun, because once we're working with the canvas, we can add anything we want to the web page. The canvas is essentially the pixels inside our browser, and we can declare how big we want the canvas to be. We can make it as big as our browser window. We can make it a defined size. We can have as many canvases as we want, well, within reason, on a page. So we're not limited to a single canvas, And we can combine a canvas with other HTML elements. We can have a canvas, we can put other things on top of the canvas or behind the canvas, because a canvas, again, is inherently transparent unless we give it a background color or image. So canvases are really flexible, and we can do a lot of really cool visual and interactive things with our web pages, even with a standard web page. So right now we're going to build widget kinds of projects that just demonstrate some of the core features of a canvas. But the expectation is you're going to take and combine the canvas with a traditional web page and put it together, so you're using it as an enhancement tool, an enrichment tool, an engagement tool, so you make your page better. Now looking at this, really basic markup in here, that the CSS, I just zeroed everything out, so it just nuked all the default margin and padding, gave the canvas a horrible red background color so we know that it's working. Then inside my JavaScript, I'm going to grab my canvas element. I'm going to set the width and height of that canvas element. Now our canvas element, the thing about it is the canvas element is just a canvas. To actually engage the pixels on that canvas, we refer to that as its context. So we have to gain control of the context, and it's the context that we actually write to. The context lives on the canvas, and the context is the pixels of it. So if we think about if we had a paragraph of text, we would say, oh, I'm referring to this paragraph. But the text inside the paragraph is generally what we're talking about. It just isn't a paragraph shell. The parent is the paragraph. The text itself is the content. The canvas is the parent. The context is the actual pixels that we will be manipulating. Now you will see it says canvas get context in 2D, because right now we're dealing with 2D canvases, and that is what we will work with. If you really want to engage with 3D, then you will look at doing WebGL. That's how we end up doing 3D. So we do WebGL 3D so that we can gain access to a 3D space if we're so inclined. That's well beyond the scope of what we're going to be doing right now. So grab my canvas, grab its context. The context is what we get to draw an image onto later when we call our draw function. And now I'm going to construct an image object. And then with this image object, we will be setting its source, and we're going to attach a listener to it. The listener, we've used add event listener before. We've used it typically for a click event or something like that. In this case, we're using the load event. So we want to have this image listen for being loaded, because we can't draw it to the canvas until it's in memory. So we have to load it first. Once it's loaded, then we call the draw function. And then the draw function is going to then be defined down here. And then we set the source of the image. So it looks, just like if we had our image inside our markup in our HTML, we'd do image source equals, and then we would be specifying that URL for it. The draw function. A couple of things are happening here. I'm going to comment that out and go back to this one. That's the one I meant to do first. So we'll take a look at that. Let's go load canvas 0. We can see that it loads the picture here. So it's now loading my sprite sheet. So it's loading my elf here, which is not a single, but is in fact 12 images of my happy little, well, maybe he's not happy. That's kind of a creepy picture. It's loading all 12 images of my elf, and we can see how that sprite sheet loads here. If we learn to manage sprite sheets instead of having separate individual image files, our asset management gets much easier. So it's also better from a memory standpoint to load all of these images in one single image file in this what's called a sprite sheet, because I only have to make one call to the server and then say I want to download this file. If I had all 12 images as separate .png files, then I would have to make 12 separate calls to the server to download 12 separate images. And when the assets are small, we will be spending more time trying to connect to the server and establish that connection and to download the file than actually downloading the image. So from a performance standpoint, if you have a bunch of small assets, it actually is better to bundle them into a single larger asset and load that one large asset. That's the performant way to do things. So the draw function says context draw an image. It specifies what image we're drawing and where to draw it on screen. Now, draw image has a few extra parameters available to it, and that's what we can look at on this next line here. So we can specify the image file that we're drawing, and then we can specify what are the source coordinates that we're drawing, and then where do I want to position that image on my screen. So now if I look at it, I will see that there's only one image present. Even though there are 12 images on that sprite sheet, now I am drawing a single image. So my source coordinates, source x, source y, source width, source height, destination x, destination y, destination width, destination height. So if I just play with these and say I'll just add a 1 to there, we'll see how it stretched that image out. It did not scale it proportionately. If I add a 1 here, it's still not going to be a proportional scale because I didn't, in this case, kind of triple it. Now if I guessed, let's see if I said 159 and then 189, so now I did an actual tripling of the image. Now I've scaled it proportionally. Because if we do something like that, we can see how these numbers are playing out. So destination x and y, destination width and height. Source x and y, source width and height. So if I wanted to grab one of the other images, I would have to do the math and figure out where on that sprite sheet I was grabbing it from. Now looking at the sprite sheet, we can see 0, 0, and then the width and height of 53 and 63 gives me my first elf. If I want to go grab the elf in the far right corner, I can do some math to figure that one out. Or we can modify it here and say 159, 189. Now if we go back and set it to its original size, so it's possible to bring in small artwork and then scale it up. And now, so that's not 189, 126. Photoshop tells me when I look down, there's 0, and then we can work our way over. So 0, and then there is 63, 126. That shows me that's the top of that next sprite. So now when I do it, we're able to see a different frame emerge in our sprite. Now this sprite also, it has a transparent background. That's why we see the red occurring around that elf. Migrating from the basic canvas to allowing us to do more than just straight draw an image onto the canvas, we're going to look at some other things that we can do to extend that. First thing I'm going to do is make a bigger canvas so I have more space in which to work, because the 3x200 is a little bit small. The 6x400 is still small, but it's enough to get across what we need to learn as we're doing this. What I want to do to be able to turn this into a more complete project, I want to be able to have more than one object that I'm working with here. So more than one version of my elf that I'm drawing on screen. So the first thing to do is to get one elf on screen. We'll get that one elf animating, and once we have one, then we can make multiple copies of that and put them on screen so we have this whole horde of elves that are animating on our screen. And that's what we'll be moving to as part of this. So to begin with, what I'm going to do is I'm going to create an object. And this object, in essence, becomes a prototype object that we are able to work with. And once we can have this prototype, we can make any number of versions of it that we want. So we can start out and say let, and then because this is the master or prototype object, convention says we will use a capital letter in our name of it, where normal variables we use lowercase. Now, what we're doing is we're creating an object prototype. In doing this, it's similar to what we do with classes. Now, modern JavaScript or ES6 does allow us to use classes, so we can actually use classes as part of what we're doing. The structure and how we form things with this is very, very, very similar to how we can do it with classes, which is similar to what we have in other programming languages. Elf prototype that I'm making is going to be similar to a class type object. We do have the option to make a class, but not all libraries of JavaScript, when you look at them, are going to use classes yet anyway, so we don't have to go down that road. We will look at classes possibly at a future date. What I want to do is set a couple of the properties and methods that this object knows how to do and how it's defined. So I am going to set some properties here, and I will say sx is equal to 0, sy is equal to 0. Now, sx and sy correspond to source x, source y. Then I'm also going to have a destination x. We'll also start that. I don't want to start that at 0. I want to give it a random position, so my elf always shows up at a random position on screen. We generate a random number by using math.random. That gives a value between 0 and 1, up to but not including 1. And then we multiply that by the range of numbers that we're working with. Now, 380 is a slightly smaller number than my whole canvas, so that allows my elf, I'm never going to have one appear entirely off screen. It's going to at least get it most of the way on screen. Now, dy, same thing, math.random. And this time I'm going to multiply it by a smaller number. I will say I didn't want 380. I wanted 580. And then 280, or 380 here. So 380, that is less than the 400. The 580 is less than the 600. So that allows it to appear on screen. And I can already see I forgot to put a comma, because what we were doing is we were having inside the curly braces of this object, I have a series of keys and values. Key and value. Key and value separated by comma, or by a colon. Key value pair separated by commas. The final one in the list will not have a comma after it, because when you're making a list of objects with commas between them, you don't put a comma after the last one. That'd just be silly. And then I'll have my sprite width. This is going to, I know, be 53 because I know how big my artwork is for my sprite. Now, when you construct your own artwork, your sprites may be a different size. They may be 32 by 32, 32 by 64, or whatever number you did when you designed your artwork for the project. So I've now designated the properties of my object. Next, I'm going to designate the methods to this object of what can it do. Properties are what it is. Methods are what can it do. So kind of think noun versus verb. Or if we were describing the elf as a actual kind of a person or character, the properties would be how big is it? Where is it located in the world? What color hair does it have? What color shirt is it wearing? Methods, or what can it do, would be, hey, can that elf walk? Can it talk? Can it attack? Can it cast a spell? Can it die? What are the things it knows how to do? Those are methods. After I have my properties with my methods, the first one I'm going to define is going to be update, and that will be a function. So we can now designate what it can do. Now, there's going to be one other method that it knows how to do, and that will be display. And that will also be a function. So you'll notice that methods have function as part of them. And this final one I don't put a comma after because it's the last item in this list of things, properties and methods. So I have an update method and a display method associated with this. I'll worry about populating those a little bit more shortly. So now I have a prototype method for my elf. And I can just simply say let e1 be equal to object dot create, and now ELF. I notice I used a capital E because I'm designating this prototype object. So I've now created this object. It has these functions and methods. Now, looking here, under the context, I want to draw from my ELF image. And now I'm going to populate these values. So instead of just being these image values, and I'm going to then instead use the values for my ELF. So I can go E1, and now my source X, E1.sourceY, E1.sprite width, and E1.sprite height. So our source X, Y, width, and height. And now I can set up my destination values, which will be E1.dx, E1.dy, E1.sprite W, and E1.sprite H. If I was resizing my artwork, I could potentially have different values from what is on the sprite sheet versus how big I want to put it on screen. Now when we look at this, it's going to do some interesting things as part of it. We also, as part of this function, I need to call requestAnimationFrame, and I'll call this draw function. Now, if we run our project and take a look at what we have going here, if I keep refreshing the page, you'll see it keeps spawning my ELF in a random location. It's time to give this ELF some method. Now, this is where we get to complicate things a little bit, because what I want to do is I want to make the ELF fall down the screen. So I want to change its destination Y. So I want to set its destination Y. I want to increase its value. So I can update that. Now, what that also means is I can then tell my ELF to update. So I'm going to tell the ELF to update. I'm going to set it so that my dy increases by 1, and if you prefer, you can do dy is equal to dy plus 1, which is the same as dy plus plus. Both of those are the same option. So now, if I save this and take a look here, we'll see that I have an error message, and it says dy is not defined at object update. You're like, what? dy is defined right here. What are you talking about? I don't understand. And what it is I've defined the properties here, but this method doesn't know what this dy is referring to yet, because we're inside a new set of curly braces. So it's losing track of, we're like, dy what? And what we have to do is give it a little bit of help and say, I want you to use this dy, and it goes, oh, you mean the one that's part of this whole declaration of this object that we're a part of. So we get to use the keyword this. We'll be using it a bunch. And now when I do it, we can see, oh, look at that. Refresh the page. Oh, look at that. Refresh. Whoa, look at that. Refresh. And we'll see that this canvas is transparent, and I'm writing the pixels to it. And a couple of things are happening. One, he's falling off the screen and not doing any cool asteroids wrapping, so we got to fix that. And two, my background isn't really kind of clearing itself properly, so we'll have to address that as well. So first we'll take care of the wrapping function, And it's not musical wrapping, but we're talking about then moving. When it hits the bottom of the screen, I want to go back to the top of the screen. And we can do that using a conditional. We can say if this.dy is greater than 400, which is the size of my canvas, this.dy is equal to, and now we have to figure out where to put it. And if I want, I can go to negative sprite h. So I'm going to negative sprite h. Well, sprite h is 63, so I put it at negative 63. Now I could hard code in 63, but it's better to leave it as using the value of the sprite, because then if I put in a bigger or smaller sprite, I don't have to change this logic. I don't have to change the value in more than one place. So that works better. So let's save this and see what happens. Okay, so far, so good. And boom, get an error. Sprite h is not defined in object update, and go, oh yeah, look, I forgot to put in that magic this keyword. So when you're defining the methods that are part of an object, it's going to be really important to make sure that you remember all of the thises. If you forget the thises, then you will get that error message. So now if I save this and run it, we'll see he should wrap when he hits the bottom of the screen and now come out of the top and continue on down. So it's working, and now it just looks like a little weird circle face moving on a green stripe, even more disturbing than before. That means I need to clean the background. I need to clean my canvas between each paint. And to do that, at the beginning of draw, that's where we want to clean that option. Oh yeah, I forgot that's what's going on there too. And another item that I need to point out as well. So cleaning out the background, we need to tell our context to clear rect, and we specify what we want to clear, because if I said, oh, I just want to clear half of it, then starting at 0, 0, I can go canvas.width, and I could just clear, say, the top 200. And if we just look at that, we'll see that the top part works, and then after it goes down 200, then we should just start getting the striping effect going on. So we can see how that works. So if canvas.width is a value, that also means canvas.height should also work. Whoop. Now if I save this, refresh, and I will see that my canvas is clearing itself between each repaint or redraw. My object is falling down the screen. All is right with the universe. Third thing to notice here is, so when the image loads, it calls the draw function. Draw function is down here. Draw function then calls requestAnimationFrame. That calls draw function, and that's how we get it to start looping. Because if we just look at the rest of the JavaScript, it's like, well, nowhere does it. We never actually called draw, but we called draw as the completion handler for this event listener. So when the image is loaded, then it calls draw. So if we have one object on screen, that's great, but I could now say let E2 equal to object.create elf, and let me just fix my capitalization there. And now that we've done that, now what I can do is say E2.update, and then I have to go through and copy this. And now let's, so I'm going to select all the E1s. Okay, it'll be easier, I suppose, to just... This is why we don't want to do it this way, because what we're going to discover is this is a huge pain. So now if I save this out and look at it, it should have put my elf somewhere else. E2, E1, E2. Let's beautify. Save. I forgot. So when the elf object is created, the first dx and y, it sets as a random value. If we want to create a new random value, then we have to set the property for that object at that time. When we do that, it now sets it with its own unique value. Now what we can see is if I have elf1, elf2, elf2 now gets these values reset. Working here, this is getting kind of ugly. If I had a third one, a fourth one, and let's say I wanted to have 20 on screen, my code would be unmanageable. It would be ugly, it would be super ugly and just unmanageable. But now we can see, oh, they're almost friends there. Oh, now they're real buddies here. They're piled on top of each other. So we can see how each time I refresh the page, they're wandering to 2 new random positions and they're animated. But this is not going to be a great way to deal with it. Instead, as we're doing this, what we want to do is have a group of elves that then we can store inside an array. An array is just a collection of similar kinds of objects. In this case, it will be the elf object. So if I say let sprites be equal to empty brackets, now we're going to populate that with a whole bunch of elves. So these lines here, I'll be reusing some of these in a moment, so I'm not going to delete them. And this is now moving into the proper way of what should be in Canvas 2, because what we realized is we have a need, if we want to have more than just 1 or 2 objects on screen, we need a better way to manage those objects. And with that, we are going to use an array of objects to handle that. So now I will create a for loop, and inside this for loop, I'm going to just start out, and I'll just do 10 with these elves on screen. And now I can populate my sprites array, and I can now say that is going to be equal to, and this is where I will go and grab that value. So now that can go away. These 2 lines here of setting the x and y, we can put those in. So I will now grab sprites I. So what we're able to do is when we have an array, and arrays are always designated with curly braces. That is the convention within JavaScript, or not curly braces, square brackets. Square brackets are how we designate an array. And within that array, I'm now going to use this for loop. So we set I equal to 0, I is less than 10. I will go up by 1 each time we go through this loop. And then in my sprites array, I will take the sprite at position 0 and set it equal to create a new elf. Then I'll take that sprite at position 0, and I'll set its dx property, so it's destination x, and then I will set its destination y property as well for that. So this is how I'm able to take my sprites array and populate it, in this case with 10 elves as part of it. Now I want to add in another value to my sprite. I want to give it a speed. I want to let it have a variable speed. In this case, I'll set a speed y. In the initial one, we'll just set it to 0. Here I will say sprites I dot speed y is going to be equal to math.random. And now we'll multiply that by 3. So this gives me a random number between 0 and 3, and then we'll add 3 to that as well. So that means my speed will be somewhere between 3, because if the random number comes out at 0, 0 times 3 is 0. So 0 plus 3 is 3. And at a maximum, it's going to be essentially 3, because if math random gives me a value of 1, 1 times 3 is 3. And then 3 plus 3 is 6. So my speed of these falling elves will be somewhere between 3 and 6. All right, so I've created an array of 10 elves. Just going to save that, go back over to my page, and we'll see, oh, E1's not defined. Oh, wait, where's E1 not defined? That'd be at line 62, I'm guessing, because I deleted what was there. So now I'm going to say E1 update. Nope, not going to do that. We don't need, I'm going to get rid of all this stuff for 2. Don't need that. There we go. That finally worked after 8,000 clicks. And I'm going to use a for loop once more to cycle through all of my sprites. So I'll say for. In this case, it's my sprites array. Now, we can use var when we're doing a for loop. We could use var, or we could converting them to let periodically. But within JavaScript, if I use var instead of let or const, that's totally fine, especially in this instance. So you could just leave it at var using the code completion to help you. So now I can see I'm going to go through my array of sprites. And the first thing I'm going to do is tell that sprite to update itself. So cycling through the array allows us, so now we can comment that out. It allows us to go through each object or each sprite that we've put into this collection of objects and tell them to do something. So now I'm going to grab that context stuff there. We'll put that in. But I need to change it, so everywhere it says E1, I'm going to have to change that to sprites eyes. So remembering that sprites is my array, the square brackets and then a number in it references the object in that array that I'm trying to access. Getting used to working with arrays is something that can sometimes take a little bit of time and practice, but eventually you'll come to understand that array is just a group or a list of things. And we can reference an object within that array by its position. The first object in that group is at position 0. The next one is at 1. The next one is at 2 until we hit the end of the array. So now, everywhere it says E1 right here, I will change that. And say sprites, square brackets I. So now we're referencing that individual item. Now we should be able to see, oh, sprite, oh, I forgot to add in my S when I did that, whoops. And that is why we always leave the console up inside of our browser so we can see when we have errors. So speed-Y isn't doing anything quite yet. We do need to modify it because currently they're falling based on 1 pixel per frame. So we need to modify that and say plus equals this dot speed y. Now when we do this, we'll see that they're all falling at kind of different speeds. And if I change it so that we have more on screen, we'll see that there's a lot of them all falling. We can start to see a layering of these weird elves falling down the screen. Moving on to the next phase, what we want to do is be able to get it so that our elf is animating on screen so that we're actually taking advantage of all of these different frames of artwork that we've created. And to take advantage of the frames of artwork that we've created, we do need to add in a few extra variables to help keep track of things. One of those is going to be our current frame. And we'll start our current frame out at 0. Then we need to know how many frames are present in our sprite. In this case, I know there are 12. I need to know how many columns are used. And I know for that there are 4. So there are 4 columns. There are 12 images that are part of this sprite. So I now need 4 columns. And with that, we're going to then be able to animate this object. Now the process for doing that, what we're going to do is we're going to say, right now we're telling it this is the source x and y, source width and height. The width and height aren't going to change. But our x, if I want to now look at the next frame in the animation, what I need to do is I now need to move my x value, my source x value, over by the width of the image. So I need to add 1 to it. And then I need to move it over again. Then I need to move it over again. Then to get back to this one, I need to reset it back to my beginning value, but I need to move my y down 1 row. So I need to change my source y, and then change my source y again, change my source x, change source x, change source x, and then reset source x back to 0, and then change my source y once more, and then change source x, change source x, change source x, and then reset both of them back to 0. So that's the number sequence that we need to work with here as we're doing it. Now, conveniently, because we are dealing with programming, there are some shorthand ways that we can work with this. So each frame, I want to update what I'm doing. So I need to change my source x is going to be equal to something. No, I don't want that. And then I need to set my source y to be equal to something. And then finally, I need to set current frame equal to the next frame. Now there's a couple of different ways that we can do that. We can say current frame is equal to current frame plus 1, and then we can find out if our current frame is equal to our total number of frames, and if so, then we can set it back to 0. So we'll write it out that way. Then I will also show the shorthand way of doing it that fits it all in one line. Now the nice part is, once you have this kind of method of how do you cycle through frames on a sprite sheet, you can copy and paste it between projects, and even if you kind of forget most of what it's doing, as long as you work with it and then just kind of make sure your variable names match, it's going to work. And the more times you use it, eventually it sinks into your head. You're like, oh, that's what's happening. That's how it works. So I can say current frame is equal to current frame plus 1. And then if this dot current frame is equal to my total number of this dot frames, this dot current frame is equal to 0. So current frame goes up by 1, but if current frame is now equal to the total number of frames, then we set it back to 0, so the next time we go through, it will be back to 0. So that's the sequence that we use. But there is a one-line version of doing it where I can say this dot current frame is equal to this dot current frame plus 1. And then I'm going to use the modulus operation, which is a math operation that returns the remainder. And we'll look at that in a moment. And we'll say this dot frames. Now, this one line is the same as these 2 lines, or if you prefer, We can break it into, or these, and comment these out. We'll get to those in a minute. So this line, these 4 lines are the same as this 1 line. If you like the 4 lines better because it doesn't hurt your head as much, use the 4 lines. If you like the single line, use the single line. I used the 4 lines for a long time until my brain finally wrapped around the single line, and now I prefer the single line and find that it's easier to look at and read. So we'll just keep 1 up there for a moment. And we don't want to do anything there. For creating the pattern for figuring out SX and SY, we have to, well, we round it down because we're going to potentially, as part of the math, not always have whole numbers. So it's always just a good practice to round it down. So we grab the current frame, and on the first case for SX, we grab the modulus, divide it by the number of columns in the object, and then we're going to take that value and multiply it by the width of the sprite. So what happens is the first time I go through with modulus is I divide these 2 numbers, and then I don't care how many times it goes in, I just do the division, and then I keep a remainder if there is one. So columns, we know there's 4 columns. My current frame starts out at 0. 0 divided by 4 is 0, remainder 0. So SX will start out at 0. The next time through, current frame will be 1. 1 divided by 4 is 0 with a remainder of 1. And then current frame goes up again. 2 divided by 4 is 0, remainder 2. 3 divided by 4 is 0, remainder 3. 4 divided by 4 is 1, remainder 0. So what you will notice is we just created a pattern of 0, 1, 2, 3. And it will keep repeating forever, just like our current frame is repeating 0 through 11. Our SX is going to be 0, 1, 2, 3, 0, 1, 2, 3, but then multiplying that by the width of the sprite. So 0 times the width of 53 is 0. 1 times 53 is 53. 2 times 53 is 106. 3 times 53 is 159. And then we go back to 0. So that is how we're able to get our X value to keep repeating on the dimensions that we need. We use the width of the sprite, the number of columns, and our current frame. Y value is going to be very similar, but it doesn't use the modulus, so we always round down, because then Floor says if there's a remainder when I do division, cut it off and use whole numbers. For animation purposes, animating on whole numbers means we're animating on whole pixels, not twixels. Our browsers are able to show us twixels or a 20th of a pixel, but we're going to get smoother animation if we keep things locked to the pixel. So we'll just have kind of better performance and better values. So now I take this dot current frame, and this time I'm going to divide it by the number of columns and multiply that by the height of the sprite. So if we picture current frame starts out at 0, 0 divided by whatever is still 0 times whatever gives me 0. The next time through, current frame is 1. 1 divided by the number of columns is going to be, well, that's 4, so that's 1 divided by 4 is 0.25. 0.25 times the width of the sprite is not... So current frame 1 divided by 4 is 0.25. 0.25 rounded down is 0. 0 times the width of the sprite is still 0. So if we go back and look at the ELF, current frame is 0. that gives me this one. Now, current frame is 1. 1 divided by 4, our number of columns, is a less than 1 value. That's still going to give us a value of 0 when we round it down. So we get to stay in this top row. 2 divided by 4, still less than 1. Rounded down will be 0. And then 3 divided by 4 is still less than 1, gives us 0. Now when we get to 4, so when we get to 4, current frame is 4. 4 divided by the number of columns, 4, that's 1. 1 times the width of the sprite puts us right here, because the height of the sprite, 1 times sprite h, will be 63. 5 divided by the number of columns is going to be slightly more than 1. It'll be 5/4. Rounded down will be 1. 1 times the height of the sprite will still be 63. 6/4. 7/4. Again. So we have 0, 1, 2, 3. Then 4, 5, 6, and 7 are here. 8/4. That's 2. So then we end up with 2, because 8/4, that gives us 2, multiplied by the height of the sprite, right here gives us the 126 that we need for our top point to give for sprites 8, 9, 10, and 11. So that is how we generate our different source values for XX, SY, how we update current frame. Now I don't need to log that out anymore. And now my sprites are going to update their display, and then they'll finally draw themselves on screen. So now if I save this and go back and watch what is happening, we'll see that that sprite is animating on screen. Now I only have one because I got rid of it so we could simplify our log statement. And if I put 100 of them on screen, we'll see that I have 100 sprites animating on screen. When all of my sprites are made, one of the things that I'm noticing is that they're all animating in unison or in sync. What I can do, in addition to giving them random speeds and positions when they start, I can also set it up so that their current frame is going to be equal to, so I have to round down math.floor, and then we'll say math.random times 12, which is the number of frames. So that's going to give me a random number rounded down, so it'll be between 0 and 11. So then I will have random frame values for my objects. And now they're not all exactly at the same place in their animation, so we start to see a little bit more variability. If I had more frames of animation, it would become more apparent what is happening with it as it's doing that. Moving into the final phase, the one that we're going to be looking at here. Previously, when we loaded the ELF image, we loaded a single sprite sheet. If we combine multiple sprites into a single sheet, the technical term is called an atlas. It's a texture atlas. So the file ELF atlas is the one I'm going to be loading now instead of loading the single ELF. So if I'm going to change, so if I say I'm going to load the ELF atlas, if I go and look at what's happening, well, nothing's changed because I haven't loaded or displayed that image into the background. So one of the things I want to do is I want to now put that image into the background of my project as I work with it. So to do that, I now need to have another object. Now with this object, eventually what we're going to learn is every individual visual object we put on screen is most likely going to be a sprite object. And they will share a lot of common characteristics. So right now we're going to do it in the messy code way. And then at a subsequent session, we'll figure out how we can actually just create a single sprite object de facto class for that nature. And all of our objects are based on that single sprite object. But for now, we're going to make a basic object that is going to be the iceberg. So to do that, to save myself some typing, I'm going to copy what is in the elf, and then I'm going to paste, and now I will change it from elf. I'll change this to iceberg because we'll make an iceberg object. Now, the x and y for this object aren't going to be random, so we will set them up at fixed values so that we can put them on screen. We will set up the destination x, the destination y at fixed values so we can put them on screen as well as we work on representing them into our project. Now, looking at the atlas, this particular image starts at 257 pixels down. So the first elf started at 0, 0. This iceberg starts at 257 and 0. So now my source y is not going to be 0, but it will be 257. My destination where I want to put this, I'll put it at 0 for now. I'll put that at 0. The width and height of the image that I want to represent on screen, I'll just say that is going to be my full canvas, 600 by 400. And it doesn't have a current, it's not cycling through frames, but it is one column wide and one frame long. So we'll just leave it. We don't need to change anything. So technically, with that, even if I do nothing with this code here, it's not broken. It's not going to, I can just leave it because we're not using it, but it's not hurting anything. Now, the update function of how I want to update it, that we are going to do something different, so I am going to just comment that out. So I've now created my iceberg object, and I need to make an instance of that object so I can add it to my group of sprites. And to do that, I can say let iceberg. Now we're only making one, so I don't put it in the for loop. I'll just do it separately, and this will be object dot create, and the object I'm creating is a capital I iceberg. And the fingers are starting to forget how to type. So now that I've made this iceberg, I want to add this to my sprites array. And to add it to my sprites array, if I'm adding a single object to my array, if I put it at the end of the list, I can just simply, when I add things to an array, I can just use push. And then I say sprites push iceberg. Now we'll see this updates and displays and then draws all sprites on screen. So let's save this and see what happens when we look at it. And we'll see that, all right, so we've got a couple issues here of where we're placing things and how we're placing them on screen. But most importantly, we're going to notice that this whole sprite sheet is positioned inconveniently because it's now down, but it's in front of all of these little elves. And that's because when we push, it adds the object to the end of the array. And if we want to put it at the beginning, the array method we use is called unshift. Now if I choose unshift and look at it, we'll now see how the elves are on top of it. So it now pushed that object to the beginning or the front of my array. So that's a good first step. So leaving this, as I mentioned, we can leave this here. It's not going to do anything. But one thing that we're not doing or taking into account is that our source y doesn't stay at 257. So it doesn't know that we need it to be offset by 257. So we have two options. One is that I can just go 257 and comment out the rest here. The other option is when we have a more complex sprite sheet, one of the things that we may do is have an offset value. So I would have an offset y value, and that is going to, in this case, be equal to 257. And then we add that in, knowing that all of our y values are always going to be offset by this dot offset y. Now when we look here, we can see how the iceberg sits correctly behind the image. So if we're creating a more complex sprite object that we want to make a universal sprite object, so then we can just select and create all the correct values for each thing. So our L for iceberg, all of them would just plug in correct values. We probably want to have an offset. If we know that this is a fixed object and it's not ever really going to move, then we can just ditch all of that. So offset doesn't matter, and we'll see we get, again, the same result. So that allows us to have one image file loaded. And when we load that image, we're now offsetting our position, knowing that this is 257 pixels down. And when we do that, it allows it to line up. Now this iceberg is looking awful boring when it's just parked here and I want it to move. And one of the things that we can do is we can modify its position. So we can modify its destination X position by a value. So if I wanted to rock back and forth, I can use the math sine function. The math sine function is a trigonometry function, and it returns, if I put a number into it, it's going to keep returning a value between 0 and 1. So math.sine returns a value, not between 0 and 1, between -1 and 1. So if math sine is always giving me a value between -1 and 1, then what we're able to do is if we feed a number into it and keep incrementing that number, it's going to just keep varying the amount, bigger and smaller, bigger and smaller. So let's see if we get any variation. And now we got nothing there because it's a little bit unhappy. We need to have one more thing with it. With this, I'm going to have my sine counter. And I'm going to start out my sine counter at 0. And then we plug that in to math sine, and then sine counter, we're going to increase it. Let's try and increase it by 1 and see what happens. And if we do that, we can see how it looks like we have an earthquake going on. It's kind of freaky. Now if I increased it by 10, we're not getting much. But now let's see, 0.5, 0.1. And you'll see where we're starting to get some movement going on here. Let's go to 0.05. Oh, I ended up with two decimals. We'll go 0.05. Let's see what that gives me. And now you can see I'm getting this nice kind of rocking motion here. I also see it's exposing the red background. So let's start our destination X. We'll start that over. Let's try -10 and see what we get. And not bad. It's giving me something. Let's try -20. So -20 looks kind of about even. It looks like we're getting kind of 20 on each side. Now, knowing that, if I were to increase the width of the window of the sprite that I'm seeing, I can start to move things. So I'm moving it over. So I shifted my destination starting point to -40. But I made the whole sprite 50 pixels larger than what's on screen. And now as my sign counter is going, we can see where we have this kind of smooth rocking motion. So if I wanted to animate a boat bobbing up and down in the water using sine waves. Now this is remembering that a sine wave is this wave that kind of perpetually is curving up and down, up and down, up and down. And it always is doing it the same amount up, the same amount down, same amount up, same amount down. That's what sine waves and cosine waves will give us. So we can take advantage of that to create these perpetual rocking motions. And then I can have my other animation happening on top.